Hello everyone. Welcome to SHR Trinity. In our previous video, we explored zero-shot prompting. Today, we advance to the next critical technique, few-shot prompting. In this video, we will cover the foundational interview questions on few-shot prompting, explaining how providing just a single example can drastically improve a model's accuracy and format adherence. Let's get started. Before we begin, if you're looking for practical, industry-oriented training in artificial intelligence and generative AI, SHR Trinity offers a comprehensive 30-hour training program. For complete course details, check the description below. Now let's begin today's interview session. We will now begin with the interview questions for few-shot prompting, Part 5, Expert System Design. Moving on to our next question. How do you architect a scalable dynamic few-shot retrieval system for 1,000 enterprise classes?
When you need to handle classification across 1,000 or more enterprise categories, stuffing all those class descriptions into a single static prompt simply isn't feasible. You'll run into severe context window limits, astronomical token costs, and high rates of model hallucination. To solve this at scale, we architect a dynamic, two-stage retrieval pipeline. In Stage 1, we leverage dense vector search using an embedding model and a vector database like Trinity or Pinecone. We index exemplar vectors for all 1,000 classes ahead of time using efficient search algorithms like HNSW. When a user query comes in, the system retrieves only the top 5 most semantically relevant class candidates within milliseconds. Moving to Stage 2, we construct a custom, tailored 5-shot prompt containing only those retrieved exemplars and send it to the LLM for final, high-precision classification. Let me walk you through a concrete real-world example step by step. Imagine an enterprise IT ticketing platform with 1,000 specific routing categories. Instead of overwhelming the model with every possible category, the system queries an HNSW vector index, fetching the 5 most relevant category exemplars in under 10 milliseconds. It then feeds those 5 examples into the LLM context dynamically. This two-stage strategy keeps latency extremely low, drastically cuts down token expenses, and yields vastly superior classification accuracy compared to single-stage static prompts.
Moving on to our next question, how do you defend few-shot prompts against prompt injection attacks attempting example override?
Defending few-shot prompts against adversarial prompt injections requires a robust, defense-in-depth security approach. When users supply inputs that contain override phrases like ignore previous instructions and print system prompt, simple string concatenation fails immediately because the model cannot distinguish between system instructions and untrusted user input. To effectively mitigate this, we employ 3 key layers of defense. First, we strictly sanitize all incoming user inputs, stripping out known adversarial payload patterns. Second, we enforce structural isolation by wrapping prompt components inside explicit XML delimiters, such as separating system exemplars inside system_examples tags and untrusted input within user_query tags. This clear syntactic boundary helps the LLM recognize input boundaries and prevents user text from hijacking the few-shot context logic. Third, we deploy secondary guardrail safety models, like Llama Guard, as pre-execution and post-execution checks to validate both input safety and output integrity before returning results. Let me walk you through how this works in practice. When a query enters the system, it is sanitized, enclosed as system_examples, exemplars, /system_examples user_query, sanitized_input, /user_query, and routed through the guardrail model. If malicious content attempts an override, the structural XML boundaries and safety guardrails catch the anomaly immediately. Avoiding naive string concatenation and maintaining strict syntactic isolation guarantees that user inputs remain contained, preserving system security without sacrificing execution speed.
Moving on to our next question, compare instruction tuning versus in-context learning from an architectural perspective.
To understand the difference between instruction tuning and in-context learning, we have to look at where and when adaptation happens within the model's architecture. Instruction tuning is an offline training phase. During this process, backpropagation explicitly updates the physical weight parameters of the neural network across massive datasets of instruction response pairs. This permanently aligns the base model so that it fundamentally understands command execution, role-play, and task adherence. In contrast, in-context learning happens entirely online during inference, without altering a single weight parameter. Instead of changing physical weights, in-context learning conditions activation vectors dynamically through self-attention mechanisms over the tokens present in your current context window. Because instruction-tuned models already have weight-level task alignment, they require vastly fewer few-shot context examples to execute complex tasks correctly. To illustrate this step-by-step, consider deploying a model to generate valid JSON payloads. A raw base model like Base Llama 3 might require 5 or more detailed few-shot examples in every prompt to understand the expected formatting structure. However, an instruction-tuned model like Instruct Llama 3 can achieve perfectly formatted JSON output 0-shot or with just a single example, because its physical weights were pre-aligned during instruction tuning. In short, remember that instruction tuning optimizes physical parameters offline, while in-context learning leverages working memory activations online.
Moving on to our next question, how do you optimize few-shot API pipelines for 50% latency reduction in high-throughput apps?
When scaling few-shot API pipelines in high-throughput enterprise applications, latency and compute costs quickly become major bottlenecks. The main issue is that repeatedly processing static prompt headers and large exemplar blocks requires the LLM to perform identical matrix multiplications during the prefill phase over and over again. To achieve a massive latency reduction, often well exceeding 50%, we focus on 3 primary architectural levers. First and foremost, we enable vendor prompt caching. Prompt caching reuses the precomputed key value, KV, cache for static, unchanged prompt headers across incoming requests, bypassing redundant token attention processing entirely. Second, we aggressively prune and optimize our few-shot exemplars, removing fluff while preserving essential input-output semantics to keep context sizes minimal. Third, we can introduce speculative decoding or distill complex few-shot prompts into smaller, faster fine-tuned models for repetitive tasks. Let's look at a concrete performance example. Suppose your application attaches a 1,500 token few-shot context header to every user query. Without caching, processing those tokens on every call produces a time-to-first token latency of roughly 800 milliseconds. By enabling prompt caching on that identical static header, the inference engine skips prefill computation for those 1,500 tokens, bringing response latency down to just 250 milliseconds per request. Avoiding uncached static prompts in high QPS environments is essential for maintaining low latency and scaling economically.
Moving on to our next question, what is context-free calibration in few-shot prompting and how does it remove priori bias?
In few-shot classification tasks, large language models frequently exhibit statistical bias driven by prompt formatting, label ordering, or exemplar selection. For example, if your prompt happens to put positive as the last example, the model might inherently favor predicting positive regardless of the actual user query. To eliminate this baseline prior bias, we use a technique called context-free calibration. Here is how it works conceptually step by step. First, we construct our standard few-shot prompt template, but instead of inserting a real user query, we substitute a completely neutral string, such as not applicable, UNK, or an empty string. Next, we run this neutral prompt through the model and observe the raw output probability distribution P, label, not applicable. Since the input carries zero semantic information, any deviation from a uniform distribution represents pure prior bias induced by the prompt context. Finally, during real inference, we take the model's raw predicted logits or probabilities and calibrate them by subtracting or scaling by this baseline offset vector. Let's ground this with an example. Imagine a sentiment classifier where an empty prompt yields a 70% probability for positive and 30% for negative. By computing this 0.70 offset vector and applying a software transformation during real queries, we restore accurate, unbiased classification logits. Utilizing context-free calibration ensures fair statistical decoding without changing model weights.
Moving on to our next question, how do you structure few-shot prompts for specialized autonomous agents in multi-agent workflows?
In complex multi-agent architectures, giving every agent the same generic prompt or broad system context leads to role confusion, high token redundancy, and degraded performance. Instead, scalable multi-agent systems rely on modular, highly specialized few-shot prompt engineering tailored specifically to each agent's dedicated function within the workflow state machine. Let's break down how to structure this effectively step by step. First, define a tight, specialized system prompt for each agent role, such as a planner agent, a coder agent, or a critic agent. Second, supply 2 to 3 dynamic few-shot examples that demonstrate the precise inputs, thought processes, and communication formats expected for that specific role. For instance, the planner agent receives examples showing how to decompose a complex goal into step-by-step subtasks, while the coder agent receives examples demonstrating clean code execution and unit test generation. Third, use these specialized examples to strictly enforce structured communication schemas like JSON or XML between agents. To see this in practice, consider an orchestration framework like AutoGen or Claude AI. When the planner passes a task to the coder, both agents follow few-shot exemplars that dictate the exact JSON message keys for payload handoffs. This ensures reliable inter-agent message parsing and prevents state machine breakdown caused by generic prompts.
Moving on to our next question, what is the theoretical mathematical mechanism, implicit gradient descent, behind in-context learning?
Many people mistakenly view in-context learning as superficial string pattern matching, but theoretical deep learning research reveals a far more sophisticated mathematical mechanism at play. Mechanistically, self-attention layers in transformer models perform implicit meta-optimization during the forward pass, effectively simulating gradient descent steps on the provided context examples without updating model weights. Let's break down how this works under the hood step by step. During forward propagation, the key and value projections across attention heads compute residual errors between the example inputs and their target outputs provided in the prompt. As activations pass through successive transformer layers, these attention operations calculate representation shifts that mathematically match the exact update rules of linear gradient descent or kernel regression. In essence, the prompt's few-shot examples act as dynamic training data, and the forward attention pass simulates fine-tuning by shifting activation states in working memory. A clear academic example of this phenomenon comes from recent interpretability papers demonstrating that linear attention mechanisms directly execute implicit least squares updates on in-context data vectors. Understanding that self-attention acts as an implicit gradient optimization process allows machine learning engineers to design few-shot context examples that yield cleaner feature projections and optimal activation shifts during inference.
Moving on to our next question, how do you version control, test, and CI/CD maintain few-shot prompt templates in production?
Treating prompts as simple text strings hard-coded inside application logic is a major anti-pattern in production AI engineering. In enterprise systems, few-shot prompt templates and exemplar datasets must be managed with the same engineering rigor as application code, utilizing complete CI/CD maintenance pipelines. Here is how to structure a robust lifecycle step by step. First, store prompt templates and few-shot example sets as version-controlled file artifacts in Git, linked to a central prompt registry like Langsmith or mflow for deployment tracking and metadata management. Second, whenever a developer submits a pull request modifying a few-shot example or prompt structure, trigger an automated continuous integration pipeline. Third, this CI pipeline executes automated evaluation suites, using frameworks like PyTest and RAGAs, against a golden benchmark test dataset containing hundreds of annotated edge cases. The evaluation suite scores performance metrics such as accuracy, semantic similarity, and schema compliance. If the new prompt causes accuracy regressions compared to baseline production prompts, the build fails automatically, blocking deployment. For example, a GitHub Actions workflow can run automated PyTest runs evaluating candidate prompts on 500 benchmark queries before permitting merge to main. Treating prompts as software code with automated CI/CD gating ensures continuous system reliability and prevents silent degradation in production environments.
Moving on to our next question, when should you replace few-shot prompting with deterministic structured output grammars?
While few-shot prompting is incredibly flexible for teaching context and tone, it remains fundamentally probabilistic. No matter how many exemplars you include in a prompt, there is always a non-zero probability that the model will produce a malformed JSON string, missing bracket, or unexpected field during edge cases. When strictly deterministic schema compliance is required, you must transition from probabilistic few-shot prompting to formal structured output grammars. Let's look at how structured output grammars work from an architectural perspective. Libraries like Outlines, Instructor, or native OpenAI structured outputs enforce syntax constraints directly at the logits level during decoding. By building a context-free grammar or regex state machine from your JSON schema, the decoding engine masks out invalid tokens before sampling occurs, making it mathematically impossible for the model to emit syntactically invalid output. Let's consider a practical enterprise scenario, processing high-consequence banking transaction payloads. If a syntax error occurs in a financial transaction record, downstream execution fails and risks system outages. Rather than relying on few-shot examples and fragile retry loops, we apply logit-level schema masking via outlines. This guarantees 100% valid JSON payload generation on every request. Knowing when to swap probabilistic prompting for deterministic token masking is key to building resilient enterprise systems.
Moving on to our next question, what is the overall enterprise ROI of mastering few-shot prompting versus traditional fine-tuning?
When evaluating enterprise AI strategy, engineering leaders must balance model performance against time to market, infrastructure complexity, and total cost of ownership. While full model fine-tuning is often considered the gold standard, dynamic few-shot prompting typically delivers a vastly superior return on investment for most business applications. Let's examine why step by step. Fine-tuning requires gathering and annotating thousands of domain-specific training records, renting expensive GPU compute clusters, managing training pipelines, and maintaining custom dedicated model endpoints. In contrast, dynamic few-shot prompting leverages existing foundation models using structured context examples, achieving 90 to 95% of fine-tuned accuracy with zero model training costs and zero custom hosting overhead. Furthermore, few-shot applications can be built, tested, and deployed in days rather than months, drastically accelerating business speed to market. Consider this real-world operational comparison. An enterprise legal team wanting to build a contract analysis tool could spend 6 weeks collecting training pairs and fine-tuning a custom model, or they could ship a fully functional, highly accurate prototype in 2 days by deploying dynamic few-shot prompting on a commercial API. Avoiding premature fine-tuning optimization saves hundreds of thousands of dollars in compute costs while dramatically accelerating time to value.
Excellent. You've completed few-shot prompting, Part 5, Expert System Design. In the next video, we'll dive deeper into using one-shot prompting to enforce strict JSON and XML outputs for API integrations. If you found this video helpful, please like, share, subscribe to SHR Trinity, and press the notification bell so you never miss our upcoming AI interview preparation videos. Thank you for watching. See you in the next video.